Okay, so hello and welcome back. So the next question that we have here is question number 11, which is let S be equal to A, B, and C, and T be equal to 1, 2, 3. Okay, so you have these two sets. We want to find f inverse of the following functions from f to s. We want to find f inverse of the following functions. From f to s, functions f from s to t. You want to find f inverse of the following functions f from s to t, if it exists. Okay. Now, number 1, we have f is equal to basically a comma 3, b comma 2, and c comma 1. Okay, so that is the function that we have, and this function is of course from s to t. So then you can say that basically f is a function from s to t, and this is basically your function a comma 3, meaning that what that means is that f of a is equal to 3, f of b is equal to 2, and f of c is equal to 1. Right? Now, basically, of course you can see that this function is, first of all, it is 1 to 1, because a is mapped to 1, b is mapped to 2, and c is mapped to 3, meaning that every distinct element of the domain of the function has a distinct unique basically image in the range, in the codomain of the function. Meaning that if you have, for example, a, b, and c here as the domain of the function, and if you have 1, 2, and 3 as the codomain of the function, as you can see, a is mapped to 3 under f. A is mapped to 3, b is mapped to 2, and c is mapped to 1. Meaning that, as you can see, your function, first of all, is 1, 1. And second of all, it is onto, because every member of this set T is the image of some element in the domain of the function. And since the function is 1, 1, and onto, so you can say that therefore f inverse exists. Now, in order to define the inverse of this function, to define the inverse of f, namely f inverse, we have, so first of all we have to define the function f inverse from the codomain of f back to the domain of f, meaning from t to s. You have to go from t to s, and also what we need to do is that basically the function has to this function basically f maps a to 3. The other function, basically the inverse or f inverse maps, for example, 3 to 1, 2 to b, and 1 to c, right? So then you can write f inverse as a function from t to s, and you can write f inverse as a set containing all of these elements as 3 to a, 3 comma a, and 2 comma b, for example, and 1 comma c, and 1 comma c. And that is basically the inverse of this function. Now, the second part of this question, we have the same two sets that we had before, meaning that S is equal to the set A, B, C, and T is the set 1, 2, and 3. And basically F is a function from S to T, defined by basically a comma 2, b comma 1, and c comma 1, and c comma 1. So yeah, as you can see, basically the function goes from this set to this set, a to 2, b to 1, and then c to 1, meaning that the function is many one, meaning that f of b is equal to 1, f of b is equal to 1, and also f of c is equal to 1. F of c is equal to 1. And so the function f is many one. And since the function is many one, you can say that f inverse does not exist. And the reason why that does not exist is that basically you have the set S and T. So you have basically A, B, and C, and that is the set S. And then you have the set T, which is 1, 2, and 3. And basically A is mapped to 2, B is mapped to, so this is basically your function f. B is mapped to 1, and also C is mapped to 1. So you can see that first of all, this element here is not the image of any element in the domain of the function, meaning that the function is not onto. And secondly, the function is many one, meaning that the image of B under F is 1, the image of C under F is again 1. So it is not 1, 1. And so there are two problems here. Now, first of all, the function is not onto, meaning that this element is not the image of any of these elements under F, meaning that if I define a function from, now this was basically, this set over here was S, and this set over here was T, right? Now, if I define a function back from T to S this way, and call it, for example, f inverse, first of all, the problem is that I don't have any way to get back from 3 to any of these elements, meaning that f inverse would not be a function in the first place, because for f inverse to be a function, basically all of these elements must be the preimage of some element in the codomain of the function. Meaning that for f inverse, this becomes the domain, this becomes the codomain, right? And so every element in the domain of the function has to be the preimage of some element in the codomain of the function. First of all, 3 is not the preimage of any element here, so this f inverse would not be a function in the first place. Second of all, even if we didn't have the problem of 3 here, we would still have another problem. You see over here, f inverse of 1 is going to give me, first of all, it's going to give me a b, and also f inverse of 1 is also equal to c, meaning that again, based on this, I do not know whether to define f inverse of 1 as b or whether to define it as c, and therefore since f is many 1, then f inverse cannot exist. So that is the problem here. And so that was question number 11. Now question number 12, we have considered the binary operations star and O. Question number 12, consider the binary operations star and O. Star and, well, star is basically this binary operation. Let me write it here as star, as a binary operation from R to R, or a binary operation on the set of real numbers, and O is another binary operation on the same set of real numbers, defined as basically star A star B. A star B is equal to this, the absolute value of A minus B, and also A OB is the same thing as A, and this is for all A and B belonging to R, right? You want to show that star is commutative but not associative. You want to show that star is commutative but not associative. And further, you want to show that O is associative but not commutative. O is commutative but not, I'm sorry, not commutative but associative. So O is associative but not commutative, and further show that for every ABC belonging to R, show that for every A, B, and C belonging to R, A star BOC is equal to A star B, O A star C. Now, if that is the case, as a side note, you can say that if that is the case, we say that the operation star distributes over the operation O. So we can say that, so this is, as you can see, A star B, O A star C. So that means that that means that it distributes this way over basically star distributes over basically O this way, right? So if that is the case, we say that the operation star, the operation star distributes over the operation O. Distributes over the operation O. And does O distribute over star? So that is basically some piece of information. And also another question is that does O distribute over star? And of course you need to justify your answers. You already know that. So first of all, the question is, consider the binary operations. Basically star is a binary operation on the set of real numbers defined by a star b is equal to the absolute value of a minus b, and O is a binary operation on the set of real numbers defined as a of b is equal to a for all a and b belonging to R. Now you want to show that star is commutative but not so associative. So to show that star is commutative but not associative, we have So to show that star is commutative but not associative, we have basically star. We said that it was an operation on the set of real numbers, right? So to show that star is commutative but not associative, we had star as a binary operation on the set of real numbers, and star was defined as a star b is equal to the absolute value of a minus b for all, of course, for all a and b belonging to the set of real numbers. So now in order to show that star is commutative, the definition that we had was that basically we said that a binary operation on a set X is called commutative. It's called commutative if a star b is equal to b star a for every a and b belonging to X. For every a and b belonging to X, that means that a star b has to be equal to b star a, and that means that the binary operation star, you could say the binary operation star, for example, on a set X. On a set X is called commutative if basically that is the case, if a star b is equal to b star a for every a and b belonging to X. Now, so over here you can simply calculate a star b here. So in here, this was a definition. So in here we have a star b is equal to basically the absolute value of a minus b, and b star a is equal to the absolute value of b minus a. And of course, you know that basically the absolute value of a minus b is equal to the absolute value of b minus a, which is equal to a star b, which is equal to b star a, for all basically for all a and b belonging to the set of real numbers. Which means that basically star is commutative. Star is commutative, right? Now we want to show that star is not associative. To show that star is not associative, we have now as a definition, we have a binary operation star. We have a binary operation star, a binary operation star on a set A, for example, is said to be associative, if A star B star C is equal to A star B star C for every A, B, and C belonging to A, right? So that is the definition that we can use here. Okay, so now using this definition and having the definition of star itself, we said that A star B is equal to the absolute value of A minus B. So now if I calculate basically A star B star C, A star B star C, A star B based on the definition that we have here is A minus B, the absolute value of A minus B. And basically we have star C here, and again over here basically we said that A star B is equal to the absolute value of A minus B. That means that this is going to be equal to, take the absolute value of this becomes A, so this becomes the absolute value of A minus B minus C, and take the absolute value of the whole thing, right? Now that is the absolute value of, that is A star B star C. Now if you calculate A star B star C, that's going to give you A star, the absolute value of B minus C, and that is going to be equal to basically the absolute value of A minus the absolute value of B minus C, and the absolute value of the whole thing. And as you can see, they are not going to be equal, meaning that A, B, and C belong to the set of real numbers, and let's assume that the absolute value does not exist. So depending on the values of B and C, for example, here you would get So let's verify for a value, for 3 values. Let's see if these have, let's create a counter example here. Let's say that, for example, a is equal to 2, b is equal to 5, and c is equal to -7, for example, right? Now this expression over here is the absolute value of a minus b minus c, and that would be equal to the absolute value of a minus b. So 2 minus 5 minus c is -7, so that's +7, which is equal to the absolute value of, basically the absolute value of 2 minus 4 is -3, so you get 3 plus 7 is equal to 10, and there you will have a 10. Now this expression over here, if I evaluate it using the same values, I will have 2 minus the absolute value of b minus c, which is 5 plus 7, which is equal to the absolute value of 2 minus 12, which is equal to -10, which gives me a 10. So I have to create some sort of situation where we have to create a counter example here. And let me check my answer here. Now I can see a couple of values here. Let's take a as 1, let's take b as 2, and let's take c as 3. If I take these values, let's see, for example, the absolute value of a minus b minus c is going to give me the absolute value of basically 1 minus 2 minus 3, which is equal to -1, so that gives me a 1 minus 3, and the absolute value of that is equal to 2. Now the absolute value of the absolute value of b minus c is equal to basically the absolute value of a, which is equal to 1 minus the absolute value of 2 minus 3, which is equal to basically the absolute value of 1 minus 1, which is equal to 0, right? So therefore you can see that you can basically conclude that basically the a star b star c is not equal to a star b star c, and therefore you can say that basically star is not associative. Okay. Now the next part of this question, we want to show that we had another relation on R, and that relation was 230. And that relation was basically the relation O, which was basically O was a relation on the set of real numbers defined by AOB. AOB is equal to A for all, basically for all A and B belonging to R, right? For all A and B belonging to R. Now you want to show that basically that O is not commutative but associative. Now if you can show that basically A star B, basically if A star B is equal to B star A, for all A and B belonging to, for example, to R, then basically you can say that star is commutative. Which means that now here basically the binary operation that we have, instead of star, of course we have O, but that's basically the same thing, meaning that if I calculate basically AOB, I can say that now AOB is equal to A for all A and B belonging to R. And BOA is the same thing as B, for all A and B belonging to R. And therefore AOB is not equal to BOA, and therefore O is not commutative. And to show that O is not associative, or actually it is associative, to show that O is associative, we have basically, so we said that if AOB OC is the same thing as AO BOC, then O is associative. Of course for all A, B, and C belonging to R. Now, AOB OC is the same thing as AOB is the same thing as A, and then you have OC, which is equal to A, and AO BOC is the same thing as AO BOC is the same thing as B, and that is equal to A. Therefore, you can say that AOB OC is equal to AO BOC for all A, B, and C belonging to R, and therefore O is associative. Now the next part of this question, so hopefully you understood this. The next part of this question is that you want to show that for all A, B, C belonging to R, you want to show that for all A, B, and C belonging to R, A star BOC is the same thing as A star B, or A star C, and as a side note, that means that basically star distributes over O. Star distributes over O. So we can calculate this the left hand side, the left hand side of this equation. If basically A star, the definitions of these two binary operations where a star b was equal to the absolute value of a minus b, and a o b was the same thing as a. Of course, for all, basically for all a and b belonging to R, right? Now, if I calculate this side of this equation, I'll have a star BOC is equal to a star. BOC is the same thing as B, basically. And a star B is the same thing as the absolute value of a minus b. And this side of this equation, and this is the same thing as this is the right hand side, this is the left hand side. Now the right hand side, RHS, is equal to a star B O a star C, which is the same thing as a star B is the same thing as the absolute value of a minus b, or the absolute value of a minus c. And you can see that AOB is equal to A. So then this is simply equal to the absolute value of A minus B, which is equal to basically your LHS. Your LHS is equal to the absolute value of A minus B, which means that your RHS is equal to your LHS, and therefore you can say that and therefore star distributes over star distributes over basically O. Now the next part of this question is asking, does O distribute over star? Does O distribute over star? Okay, so basically to check whether O distributes over star, so here we have so I have written the same basically. Over here we have a star B BOC, and over here instead of a star BOC I've written a OB star C, and if that is the case, then that would be AOB star AOC, right? So this distributes over AOB and AOC, and star would be here. So now you know that basically the left hand side, the LHS here is equal to AOB star C, and that is equal to you can simply write this as A. It doesn't matter what this is, as long as you have AOB, that is equal to A, so this is equal to A. Your RHS is equal to this whole expression, which is AOB star AOC, which is the same thing as A star A, which is the same thing and the absolute value of A minus A, which is equal to 0. So which means that your basically your LHS is not equal to the RHS, and therefore basically O does not distribute over star, right? So this was question number 12. So the next question is now question number 13. Question number 13, we have given a non-empty set X, given a non-empty set X, given a non-empty set X, let star be an operation on P of X. Let star be a binary operation on P of X. So P of X times P of X to P of X be defined as A star B A star B is equal to A minus B union with B minus A for all A and B belonging to P of X. A and B belonging to P of X. I want to show that the empty set phi is the identity for the operation star. I want to show that the empty set phi is the identity for the operation star. For the operation star, and all the elements A of P of X and all the elements A of P of X are invertible with A inverse is equal to A. And there is some hints at the end of the question that we probably don't need them. So you have a non-empty set X, and basically star is a binary operation on the power set of X, meaning that basically suppose that your X is, for example, some set like, for example, 1, 2, and 3, and all the possible subsets of this set are going to be, for example, the set containing 1, the set containing 2, the set containing 3, the set containing 1, 2, 2, 3, 1, 3, the whole set, the null set, and so on and so forth. That means, and then basically if you put all of those sets together and collect them in one single set, that set would be the power set of X, basically. Which means that the power set of X, or P of X, is going to be a set containing all of those sets. For example, the set containing 1, the set containing 2, the set containing 3, the set containing 1 and 2, the set containing 1 and 3, the set containing, for example, 2 and 3, and the set containing everything that we have in the set, 1, 2, and 3, and the null set. These are all of the possible subsets of this set, 1, 2, 3, 4, 5, 6, 7, 8. That's 2 raised to the power 3. So you have 8 sets here. 8 is the same thing as 2 raised to the power 3, and this 3 is the number of the elements of this set. Right? So what that means is that now this is your P of X, and so the binary operation is basically from the is basically on this. The binary operation is on this, on the set P of X. Is on the set P of X, which means that okay, so basically a binary operation. So when we say that we have a non-empty set X and then star is a binary operation on this set, and defined by, for example, by this relationship, what that means is that basically normally binary, as you know, it means binary means two, means related to two, I would say, or you could say in some way related to two. Binary, as you already know, bi means refers to two. For example, you know that tri refers to 3, quad refers to 4, or PEN, I think PEN or PENT, something like that, refers to 5. HEX refers to 6. These must come from some language. I don't know what language that is, probably Greek or some other language. And you have pentagon, hexagon, and then you have heptagon. HEP must refer to 7. I'm not sure about these, but basically you know that for binary we already know what that means. When we say a triangle, we have a triangle, meaning 3 angles. We have a word, for example, like quadrilateral, which means that a flat geometric shape that has 4 sides. Or we have a pentagon, for example, which is a flat geometric shape. A polygon that has 5 sides, for example. We have a hexagon that has 6, a polygon that has 6 sides. We have heptagon that has 7 sides, octagon, nonagon, and so on and so forth. So bi basically refers to 2, right? So a binary operation. So when we have a binary operation, that means that this operation operates on 2 operands. So you can say that a binary operation operates on 2 operands. Now, what an operand is basically, for example, when you write 2 plus 2 is equal to 4, addition is a binary operation. Is a binary operation in mathematics, right? Now, the 2 operands that we have here are 2 and 2. These are the 2 operands that we have. Or when I write, for example, A times B, then whatever that is, basically my operands here are A and B. So these are my operands. And the multiplication, this is again a binary. This is again a binary operation. By the same logic, so you have addition, you have multiplication, you have subtraction, and you also have division. So these 4 binary operations we already know in mathematics from class 5, class 6. Now, And of course, you can basically, you can have, for example, 2 plus 3 plus 5, but basically doing this calculation is not possible if you want to do all the three of them together, meaning that you have to, for example, add 2 and 3 first and write this as 5 plus 5, and then 5 plus 5 is equal to 10. That means that basically addition is a binary operation. First you have to do this part and then the rest of the operation. And the same goes for every other binary operation that we have here. Now these binary operations that we define on these sets is a more general way of talking about these binary operations that we had before, meaning that as a general definition, meaning that if you want to have a general definition, which can cover all of these four operations, which can cover all of these four operations, what you can do, basically, we can basically the set of numbers is to be replaced by an arbitrary set X. So we can replace the set of numbers, replace the set of numbers by an arbitrary set X, and then general binary operation is nothing but association, and then basically we have a general binary operation, which is nothing but basically association of any pair of elements A comma B association of any pair of elements A comma B from the set X to another element of X, And what that means is that basically suppose you define a binary operation on some set, for example X. Then how that works is that basically the binary operation, we write it this way, meaning that we write it star, for example. It could be any other symbol or letter or whatever you might have. Star is a binary operation on a set, for example X. So basically you have to calculate the Cartesian product of X and X, and that goes to X. That means that this basically this ordered pair A comma B comes from this set. This is the Cartesian product of X and X, and then through this operation, this ordered pair is then associated with another element of X. For example, if I say that, for example, star is a binary operation on the set X, And suppose that, for example, the set X is, for example, these elements like 1, 2, and 3, right? So then the Cartesian product of X and X would be all of these elements like, for example, 1, 2, you have 1, 1, you have 1, 3, you have, for example, 2, 1, you have 2, 2, you have, for example, 2, 3, then you have 3, 1, then you have 3, 2, and then you have 3, 3, right? And this would be, basically, these are all the ordered pairs that you have in the Cartesian product of X and X. And the set X is again basically this set over here, right? Now, in order for this binary operation to be defined, this has to be a function. This must be a function. This must be a function. Meaning that, for example, let's say that I can say that A star B is equal to, for example, A minus B. If I define the binary operation star this way, then and of course that has to basically apply to for every A and B belonging to X, for example, in this case. So what that means is that, for example, then if I calculate the, for example, A star B or 1 star 2, I can write the star of 1, 2, I can write it this way, or I can write 1 star 2, that is equal to basically 1 minus, based on this 1 minus 2, which is equal to negative 1. And as you can see, negative 1 doesn't exist here, so this is not a function based on this. So you have to define it in such a way that this actually remains a function. And when you do that, if that is the case, that basically that this is a function, then the binary operation star is defined, and then technically what we say is that basically, let me write this over here. Then technically what we say is that as a definition, we say that the binary operation star, a binary operation star on a set A is a function. It has to be a function, basically star as a binary operation on the set A, and we denote star of A comma B by A star B. Okay, that's basically the whole story there. Now, star can be any sort of mathematical operation that you might have, and then you can define whatever you want using this concept of binary operation. So what that means is that through all of these basically through the rule that we have here, for example, here we are saying that basically star is a binary operation on P of X, and I wrote the set P of X over here, and we defined it as A star B is equal to this relationship between A and B over here, and we want to show that the empty set phi is the identity for the operation star, right? So what that means is that basically this operation star is basically taking is taking now of course as you can imagine, you need to take the Cartesian product of P and X and itself, meaning that the Cartesian product of P of X and P of X would then in turn be a set that contains all of these elements, meaning that you would have, for example, this set would contain, for example, the set containing 1, comma, for example, the set containing 1, right? So that would be one ordered pair. And then you would have, for example, the set containing 1 and the set containing 2. And then you would have, for example, the set containing 1 with the set containing 3, and so on and so forth. And you take, basically, you need to take each and every, for example, you start with this element, you take it with this one, 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 and all the way up to the end. Then you need to start from this, the second one, take it with the first one, with itself, with the third one, with the fourth one, with the fifth, and so on and so forth. And then you need to do this thing for each and every one of these elements. And then that would be, then as you can imagine, you'll get 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 8, which is equal to 64. You would get basically 64 elements here, 64 ordered pairs. 64 ordered pairs here. All of these elements basically taken together. And then what star does is that it associates these ordered pairs with some, basically with some element in P of X. So one of these elements will be associated with one of these elements in this set, and that's basically all that star does. Now that we understand what basically the binary operation actually is, now let's go through the example and the problem and solve it. So we want to show that the empty sets, basically phi, is the identity for the operation star. Is the identity for star, right? Now what that means is that as a definition, we said that basically the given a binary operation star on a set A, an element E belonging to A, if it exists, is called identity for operation star if A star E is equal to E star A is equal to A, for all A belonging to A. So that means that if the null set is the identity for the operation star, so we have A star E, which is the identity element, must be equal to E star A, and that must be equal to A. Now here, if I'm saying that basically the identity element is the null set, then this must be, for example, some element basically some element related to some element belonging to P of X, some element belonging to P of X, let's call it A star, basically the null set, that has to be equal to the null set star the same element, and that has to be equal to A, right? Now let's see if that is true. So here we are saying that A star B is equal to A minus B union with B minus A. So if I calculate A star phi here, A star phi is going to be equal to A minus phi union with phi minus a. Phi minus a, right? So phi is basically the null set. So if you're subtracting the null set from any set, you'll get that set itself. So that is equal to a. And then you'd have to take the union of that with basically the null set, subtract from that some set a, right? So you know that the null set has nothing in common with any other set, and therefore you cannot subtract any elements from the null set, meaning that whatever you subtract from the null set, you're going to end up with the null set, which means that you have a union with the null set. Now a union with the null set is always equal to a, because the null set has no elements, so whatever you take the union of with the null set, you're going to get you're going to get the same set, right? Now this is a star phi, which is equal to a, so here we have no problems. Now on the other hand, we have to show that basically this was a star phi. We have to calculate phi star a as well. So phi star a is the same thing as, based on this, we have phi minus a, and we take the union of that with a minus phi. So again, whatever you subtract from the null set, you are going to end up with the null set. Take the union of that with, basically subtract the null set from any set, you're going to end up with the same set. And take the union of the null set with any set, you're going to end up with the same set. So which proves that basically a star null set is equal to null set star a, and in both cases it's equal to a, and therefore you can say that star is commutative. I guess that's what we wanted to. No, I'm sorry. We wanted to show that basically the null set. We wanted to show that therefore basically phi is the identity element. For the operation star. Right? So let me take a look at the solution here. No, not this one. This was question number. Okay, so the next part of this question is that we want to and basically we want to show that all the elements A of P of X are invertible with A inverse is equal to A. So if you want to show that all the elements A of P of X are invertible with A inverse is equal to A, as a definition, we said that basically given a binary operation star with the identity element given a binary operation star on A with the identity element E in A, and we already found the identity element which was the null set here, an element A belonging to a set to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to B star A is equal to E is equal to the identity element, and then B is called the inverse of A and is denoted by A inverse. So now here basically we have now established that that E or the identity element does exist in P of X, so we have no problem with that. So since E exists in P of X, so then I can say that basically I can say that an element A belonging to P of X, I can say that an element A belonging to P of X is invertible if there exists a B belonging to P of X such that A star B is equal to B star A is equal to to E, which is in this case equal to the null set, right? So what that means is that now here basically we said that A star B based on the definition that we had, we said that A star B was equal to basically A minus B union with B minus A for all, of course, for all A and B belonging to P of X. Now, and now here I want to show that basically we want to show that that every element of P of X is invertible with A is equal to A inverse, or A inverse is equal to A. That's basically what we want to show here. A inverse is equal to A, which means that the inverse of whatever the element, for example, take the element A belonging to P of X, then if I take any element A in P of X, the inverse of that element is going to be itself, meaning that if I write A star A, which is basically A star the inverse of A, that must be equal to the null set, right? So if I calculate this based on the rule that we have here, we have basically A star B is equal to this, so A star A is going to be equal to A minus A union with A minus A, and that A minus A is the same thing as the null set union with the null set, and that is equal to the null set. And that means that basically, and of course we have now checked both sides of this rule over here. We said that A star B must be equal to B star A must be equal to the null set. So if you write A star A, well, again, it's the same thing as A star A in the other way around, and in both cases you'd get the null set. That means that, which means that all elements A, which means that all elements of A, all elements basically, which means that all elements A belonging to P of X are invertible with A inverse is equal to A, right? Okay, so that was question number 13. So I'll end this video here and we will continue the questions in the next video. I'll see you in the next video. Thank you.